You have to get through one class today, talking. Concavity and points of inflection. Different from points of infection. For each curve below, draw tangents at various points along the curve. So we've got a concave up, and we'll pick some points and we'll draw some tangents. So there's a point, there's a tangent, there's a point, there's a tangent, there's a point, there's a tangent. And the concave down, well, there's a point, and there's a tangent. There's a tangent. Actually, it's more of a secant because I kind of cut it in more than one place. But that was an accident. So, a function is said to be concave up on an interval I if it lies above all of its tangents on I, right? Like on the interval. And a function is, and it'll hold water too, right? That's why I think concave up, it like holds water.
Yeah, why not just go concave and convex?
Well, because it's all on your orientation, right?
I guess, but up and down are also based on orientation.
Yeah. Well, so it's like a cave, and it's whether it's up or down. Function is.
Harold, shut your damn mouth.
You'll be picked up by the. A function is concave down on an interval I if it lies below all of its tangents. A point on a curve is called a point of inflection if the curve changes from concave up to concave down or concave down to concave up. So run along this curve from left to right and mark the points of inflection. So where there is a change in concavity, so you could say, well, okay, I mean, this curve here is concave up, but then it changes about here, and now it's concave down, and then it changes about here, and then it's concave up. And it's still kind of concave up, and then it changes around here, and it's concave down.
Would there be a point of inflection at 6?
Well, there is a change, sort of, right? But I mean, it's not changing concavity, right? Because they're both concave up on either side. But yeah, we'll say, hey, there's something going on at 6, obviously. State the intervals where the function f of x is concave up and concave down. So it's concave up from where to where?
1, 2, 3, and
Let's go left to right, just for the heck of it. I mean. So it's concave up starting at -4 to 1, and not there, but from 3 to 6, and not there, but 6 to 9, right? And where might it be concave down? Well, probably where it's not concave up. So concave down from 1 to 3. And anywhere else that there's is changing to concave down, or it is concave down?
12 to 9.
From 9 to yeah, wherever, right? I mean, we don't. Yeah, so infinity, if there were an arrow on there, and there really isn't, I guess. So, but the scale is really not a very good scale. You'd think with using a computer you could get a decent scale out of here, but if that's 3 units, then that's more than 3, and that's 2, whatever. Just here, put an arrow in there, and then now. Note. Changes in concavity do not always occur at a point of inflection. A change in concavity can also occur over a vertical asymptote. For example, the graph of y equals 1 over x, shown, changes from concave down to concave up over the asymptote, right? So we need to be looking at asymptotes, right? As that's possible places where there could be a change. If we are given the equation of the function and not its graph, how do we know where the function is concave down or concave up? How do we know where the points of inflection are located? So if it's concave up, you know, as we go from left to right, the slope of the tangent is, so it starts off negative, then it becomes 0, and then it becomes positive, right? So it's a larger negative value, and then it's getting to be smaller negative values until it hits 0, and then we got some small positive values getting to larger, which means that f prime of x is increasing, right? So what are these slopes, right? I mean, they're the slope of the tangent line, which is f prime of x, and it's going from negative to 0 to positive. It's increasing. Since f prime of x is increasing, this means that its derivative is, not if it's increasing. So think of its derivative. It starts negative, goes 0, goes positive. So what are you going to say about its derivative? It's positive, right? Okay, so remember, its slopes are going from negative to 0 to, wow, it's very moving. Note that as we go from left to right, the slope of the tangent goes, well, we got large positives, and they're slowing down, they're getting smaller positives going to 0 and then negative, which means f prime of x is decreasing. Since f prime of x is decreasing, its derivative is
Anti-positive?
Anti-positive. We'll just call that negative. The test for concavity, not a real test, well, I guess in a sense. If f double prime of x, so if the second derivative is greater than 0 for all x on an interval I, then the graph of f is concave up. Right? Up. And if f double prime of x is less than 0 for all x on an interval I, the graph is concave down. Yeah, wasn't much choice there.
Right. Can't you just do it with f prime at x? If f prime at x is going to be increasing anyways, doesn't that mean it's also going to be positive? And then you can just look at f prime at x and see if the
Well, f prime of x will give us whether there's a max or min, which does actually tell us about concavity, right?
Yeah.
But it won't tell us in a particular interval, like where does the concavity change, right? We can't get that from the first derivative.
Okay.
Okay? But if we know that we're going from concave up, by looking at the second derivative, we say, here, in this interval you're concave up, and in this interval you're concave down, then that says, well, then right at this point here, what's going to be there? As you
Okay.
change from concave down to concave up, you have your point of inflection.
Yeah.
Okay. So use derivatives to show that f of x is equal to 3x squared. Oh, sorry, f of x is concave up everywhere. So what do we have to do to show that? Yeah, so we got to find the second derivative. So we'll just start with f prime of x. And then we get f double prime of x, which is 6. And what can we say about f double prime of x? It's positive, which means that so this is positive, which means that it's concave up. Hereinafter abbreviated as CU. Now, if you think about it, I mean, that's just a basic quadratic that opens up, right? So obviously that's concave up. Quadratics are either concave up or concave down. There will be no change in concavity, right, in quadratic. Now you get to a cubic, and then, yeah, all of a sudden you can change, right? You don't have to change. Actually, with a cubic, I guess you do have to change at some point. Discuss p of x is x to the fourth minus 4x cubed minus 8 plus blah, 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 in terms of concavity and points of inflection. Okay, so what do we have to find? So p prime of x and then p double prime of x, right? And then basically what we're going to do is put everything together, and by the last example today, we'll be doing curve sketching, right? Like we're going to look at everything that we've looked at to this point, put it all together, and say, now we can really draw a fairly decent sketch of this curve. Okay, so what do we got? 4x2 is 12. Okay, so if we were looking for max and mins, we'd set that to 0. It doesn't not exist, right? It exists everywhere. It's a polynomial. But we're not. Okay, so we're taking this a step beyond. Okay, so we can say that the second derivative does exist everywhere, right? What we're interested in is, where is it 0? And then we're going to look on either side of those intervals, right? Or we look at all the intervals and say, okay, is it positive in this interval, which means if it is, then the curve is concave up. And if it's negative in an interval, then it's concave down. And what's happening at the break between the interval, when this thing is equal to 0, well, if you're changing from concave down to concave up, then you have a point of inflection. Okay, and that's what we're going to look at here. Okay, so we need p double prime of x equals 0 leads to what? So 12 minus 2x minus 3, so that's equal to 0. So that's equal to 0. So we know that we have to be looking in the interval below -1, between -1 and 3, and above 3. So, all right, fine, let's do that then. Let's make a little chart here. We'll say, so I'm interested in below -1, between -1 and 3, and above 3. I've got the factor 12, and I've got an x minus 3, and I got an x plus 1. And taking those together gives me the sign of p double prime of x, which means that I can then make some statement about p of x, right? And I'll be making that statement about its concavity, right? Concave up, concave down. Okay, so we just got to fill this in, x minus 3, well, I'm going to subtract 3, and I think that, and then that add 1, and that might do it. So in this interval, so below -1, what can we say about p of x? Whoops. It's concave up. So, my bad. Okay. And between -1 and 3, it will be. And above 3, it is concave up. Okay. And so what is happening at -1? There's a point of inflection, right? So POI. And what is happening at +3? There's a point of inflection. Okay, so what did they ask us? So in terms of concavity, so we could say it's concave up from -infinity to -1, and from 3 to infinity. On that interval, it is concave down on the interval from -1 to 3. There is a point of inflection at -1. And what, right? So we got to put -1 in here. Okay, so I guess right, squeeze that in. What am I going to squeeze that in? So what do we got? -1 to the 4th. All right, now let's do this. So y is equal to -1 to the 4th minus 4 times -1 cubed minus 18 times negative 1 quantity squared plus 5 times negative 1 minus 1. Okay, so 1 plus 4 minus 18 minus 5 minus 1. 1 plus 4 is 5. Where's that? Negative 19?
Yeah.
Okay, so that's negative 19. So the point then is what? Negative 1, negative 19. And 3, right? Positive 3. So x equals 3. Extend the page. So 3 to the 4th minus 4 times 3 cubed minus 18 times 3 squared. 3 minus 1. Gotta do a little arithmetic here. We got 81. 27, 108. 9 times 18, I think that's also 108. Plus 15. Alright, so negative 217 plus 15, negative 202. Really? Oh, wow, alright. Alright, so what's that give us then? Negative 270, negative 271 plus 81, so it's like negative 190. Plus 15, negative 175 or something? Good. Yeah, I can't look on here because I just got it wrong. All right, so then we have the point 3 and negative 175. And that's it, right? That's all it asks for. Okay, so we could graph that. I mean, obviously we kind of have to zoom out a bit, right, if we want to see points of inflection. Do you want to see it? I mean, should we just go into decimals and graph it? Okay, why not? Sure. Okay, so how do we want to zoom? Out. 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 Move. Well, at this point, we should probably be setting y. Yeah, so let's say we go x from maybe negative 10 to 10. Will that do it? Yeah, that's kind of not bad. And what do we need to go down to? Negative 175? Okay, so let's go negative 200 to... We didn't really have to go that high, did we? Go in. Why?
Press the X.
Press the X.
Holy what? This is
Wait.
more than unfair.
Okay, so somewhere around here is a point of inflection, and where was the other one? At negative 1? Yeah, I think, right? So we've got concave up on the interval from negative infinity to negative 1. We have concave down on the interval from negative 1 to 3, and then concave up on 3 to infinity, right? So you've got the point of inflection, it's changing there, okay? And changing direction, right? And then it's changing direction there as well. All right, cool. Okay, let's clear this off in case we need to come back here. Actually, let's, what can we do here? Delete all. Okay, we'll just go back to a, in case we want to graph anything else. Discuss. G of x is negative 1/8. Negative? Yes, 1/8. Sine of 2x plus cos x for x lying between negative pi and 2 pi in terms of concavity and points of inflection. Excuse me, so what do we have to find? Second derivative, right? So remember, we're just right now, I mean, this lesson is just focusing in on concavity, right? Well, I think the next example after this is where we will put it all, we'll put it all together, right? Just do the full analysis of, okay, here's the equation. what do we do? That's on the last page. Okay, so we need this. God, I can't remember the rules anymore, right? So what do we got? Negative 1/8 times 2 cos 2x plus, no, minus sine x. Yeah? 2/8 for negative cos 2x over 4 minus sine x. Yeah, it's not I mean, this, yeah, right, it's not product, it's a plus.
Well, it's the constant rule.
Yeah, it's just constant, negative 1/8, right?
If you do product rule, then the other one just ends up being 0, and then you multiply it 0.
Yeah, you can, but yeah, it's sort of, at the point you get to the times 0, you, oh wait, never mind. Yeah, kinda. All right, so, okay, it might be better off writing this as negative 1/4 cos 2x in terms of doing the second derivative, right? So now what do we get? Negative 1/4 times 2 times negative sine 2x plus minus cos x. So what's that? Oh, we got 2 negatives there. So sine 2x over 2 minus cos x. So you verify that. I mean, or does that match up with what you've got? Okay, good. So what do we need then? Well, we need to know when that is 0, right? On that interval from negative pi to 2 pi.
Would it make sense to simplify sine of 2x to 2 sine x cos x, take out 2, and then factor out the cos x? And then
Yes.
you get cos of x times sine x minus 1?
Yes. We have to do that, really, right? Okay. I mean, otherwise, how else do we find out where it's 0, right? You're sitting there saying, oh, well, sine 2x over 2 is equal to cos x, and yeah, so you don't want to mix your sign. So yeah, exactly, right? We're going to say, so what do we got? We've got 1/2 of, what is it, 2 sine x cos x?
Yeah.
Minus cos x, okay, so half. And we factor out the cos x and get sine x minus 1. Yeah, we need that, right? Okay, because that's easy to do now, right? So now we want g del prime of x, so we want it to be 0. Which means that cos x is equal to 0. And we've got the interval to worry about, right? Negative, what's sine look like? That's sine. That's cos. Okay, that's like 0. 2, oh, we need like pi over 2's, right? 3 pi over 2, negative pi over 2. Okay, so cos is 0 when we got what? Negative pi over 2, and 3 pi over 2. So x is negative pi over 2, pi over 2, and 3 pi over 2. And then what else? So sine x minus 1 equals 0, sine x is 1, pi over 2. All right, good enough. So say x equals pi over 2. So now we can do our interval table. Yes, thank you. Somebody was looking for videos on exponents. This one. Okay, so what do we got? So negative pi. So negative pi over 2, pi over 2, 3 pi over 2, and it all ends at 2 pi, right? So we're in the interval from negative pi to 2 pi. Okay, so I'm just putting those guys on here. And what was our factors? There was cos x and sine x minus 1, which will give us the sine of, perhaps we should use the word polarity, right? Because we already have a sine in there. Which will then give us the concavity of g of x. All right, so which one? Cosine was this guy. So negative pi over, so it's positive, and it's negative in this interval. So it's positive, negative. Oh, no, wait, that's
Yeah, it's
negative.
the other way around. It's negative.
Yeah. Negative. Okay. Sine x minus 1. That's like always going to be negative then, right? Because sine x can only go up to 1, so if we're subtracting 1 from it, then the highest it can get is 0. Plus minus, plus minus. All right, so what are we saying about g of x in this interval? And then it's, which means that here, here, and here are all POI, right?
Are we ever going to have like the zeros for for like the double prime
Yes.
that do not cause a point of inflection?
Yes.
Okay.
You can be concave up on either side of it.
Okay.
Okay, so just think about 1 over x squared or something, right?
Yeah. Oh, okay.
Okay, so then, right, what we're doing in terms of concavity and points of inflection. Okay, so concavity then, so we could say it's concave up on the interval negative pi to negative pi over 2 and pi over 2 to 3 pi over 2. And it's concave down negative pi over 2 to pi over 2. And where else? 3 pi over 2 to 2 pi. And there are points of inflection at negative pi over 2, pi over 2, and 3 pi over 2. And so we got to go figure those out, right? What do we got? Negative 1/8 sine 2x plus cos x. Okay, so g of x is negative 1/8 sine 2x plus cos x. So negative pi over 2, negative 1/8 sine pi plus cos, negative pi, right? Fix. Sine, so 2 times negative pi over 2. So the sine of negative pi plus the cos of negative pi over 2. So that's 0, and the cosine of that's 0. So that's 0. So negative pi over 2, 0. G of pi over 2. That's actually going to be the same, right? It's just flipped positive.
They all end up being 0.
They all end up being 0. Right, so yeah, the working out of this is left as an exercise for the reader, if you were actually reading this in a book.
So is like writing CU and then the information acceptable notation for the test, or do we need to write out like the full sentence? This thing is concave.
CU is,
Okay.
yeah. We'll take that as an acceptable, we said what? That's a point of inflection, as is that, as is that. So we should be concave up on the interval from negative pi to negative pi over 2, and from pi over 2 to 3 pi over 2, concave down here and here. Oh, that's off the out of the window, but still 2 pi there. Points of inflection. And then you got your max and your mins, right? But you would have to do the first derivative there, right? We'd find out where is the first derivative of 0. So we've got a horizontal slope. All right. All right, let's clear that out. And do it all. Okay, so the full meal deal. Not quite, but there's actually a couple things I'd want to add to this, but what do we got? So for f of x, determine if there's any symmetry, right? Now we can use symmetry in sketching a curve. Okay, because if we know that it's symmetric about the y-axis, which is what kind of symmetry? Even, right? Then we know that, hey, if I sketch to the right, then I just need to reflect that. Okay, so I don't need to worry about what's happening on the left. It's even symmetry. If it has odd symmetry, then again, I can just sketch from the origin to the right and then reflect that. I like to think of it sort of a double reflection, really, right? It's reflected in the y and then in the x. But that's same as a rotation of 180 degrees about the origin. So that would be odd symmetry. So I want to add 2 little things here to this. So first, what's the domain of this function?
X doesn't equal negative 1 or 1.
Wait, no.
Yeah, it's x squared plus 1, right? So it's never not defined. It doesn't not exist. So there are no vertical asymptotes, right?
Except when it's imaginary.
Yes, if you can imagine that. What else should we know? If we want to sketch this, then let's take a look at intercepts, right? I mean, so what's the y-intercept? 0, right? So y-intercept, you set x to 0. So y-intercept, 0. What's the x-intercept? Yeah, 0 again, right? So 0, 0 is a point on it, right? I mean, so if you make this 0, then what? Then x has to be 0, right? Because this will never be 0. At the least, this is 1. So the only way to get 0 here is have 0 there. So that's a couple of things that it's handy to know before we get into the whole formal, all right, now let's determine if there's any symmetry. So that's a couple of steps I would add to this whole curve sketching thing. Okay, then we've got A. So any symmetry. So what do I do to get symmetry or to see if there's symmetry? We have to work out f of negative x, right? And if it's equal to f of x, then we know it's even symmetry. And if it's equal to negative f of x, then it's odd symmetry. And if it's equal to neither, then it's neither. Okay, so f of negative x, we just replace every x with a negative x. We get negative x over negative x quantity squared plus 1, which is this, and then this, and then this. And so what do we say? Odd symmetry. Okay, so reflection about the origin. Okay, you don't need to add that, right? I mean, you can just say odd symmetry. You can add that if you like to. What can we say about the vertical asymptotes? There are none, right? What do you need for a vertical asymptote? You need to have 0 in the denominator, right? It doesn't exist. So none. Horizontal asymptotes. So we take the limit as x approaches plus or minus infinity of the original function. And we may know what it is, but we should show what it is. So we're going to divide by the highest power of x, right? So x over x squared over x squared plus 1 over x squared. And what's that give us? 1 over x 1 plus 1 over x. So, what do we get? 0 over 1, right, which is 0. Now, do we have any other information? Like, how does it behave at positive infinity? Like, you can come at 0 from above or from below, right? Or they could both be from above or both below. So figure out, just say, as we go to positive infinity, how are we coming at 0? As we go to negative infinity, how are we coming at 0? Yes. Part of yes is huh? Yeah, you're not telling you yes. Yeah, I shall. You tell somebody yes, and they still go on with the but. And here's the reasons why you should say, I already said yes. Okay, so do we know anything as we go to positive infinity, or is it coming from above or below? So, positive, so this is 1, right? Whether you're adding a very small positive or negative, this is going to be positive, yes? Okay, so as we come at positive infinity, this is going to be positive. As we come negative infinity, this is going to be negative. So from positive infinity, so say approach positive infinity from above and negative infinity from below. It's almost moot. You don't really need to write that. I mean, doing that, at least you won't be surprised. But I mean, once you've drawn the points, then you'll see that, yeah, okay, obviously we have to come from below, because when we're to the left, we are going to be below the axis, right? So if we're then approaching the, whatever that axis is called, the x-axis, then, yeah, obviously we're going to come from, above or below. C. What's C? Determine the intervals of increase and decrease. Okay, what do we do next? Take f prime of x, right? Then we find out where it doesn't exist and where it's 0, and then we do the analysis, right, of the little chart with the signs, and then we say, little arrows, ups and downs, and we get local max, local mins. Right? Okay, so f prime of x. Is it f? It is actually f, isn't it? Okay, so 1. All right, so there's a semi-cleaned up version of it. So is there anywhere that f prime of x does not exist? No, because we can't make the denominator 0, right? And we already know that because we have no vertical asymptotes, right? So if there's no vertical asymptotes, then this has to be continuous. So now we're interested in, all right, when is f prime of x equal to 0? Well, what's x? Say it. 1 minus x squared is equal to 0. We can say that here. So when the numerator is 0, right? So if x is plus or minus 1, okay, and you don't need to go to all the detail, right? You can just say x is plus or minus 1. I'll let you make that leap. Okay, so plus or minus 1. So negative 1, 1. We've got a 1 minus x squared. We've got an x squared plus 1 squared, which is going to give us the sine of f prime of x, which will give us some information about f of x. Okay, so below negative 1, I'm going to have like a big number, and I'm going to go 1 minus a big number, which I think is going to be kind of negative. And at 0, I'm going to be like positive and subtracting, and then it'll be negative, and then that's always positive. Okay, so come to that conclusion, or say, no, you're wrong, it should be different. Oh, right, new formula sheet. Great, that is not enough formula sheet. Okay, is that good, or does that need changing?
Still.
Yes, no, maybe?
All this whole assumption there, but it's so bad, like, you don't need to go to I don't know.
All right, let's go with sure, that's fine.
Inflections, it actually does that shit. It is advanced, but you're welcome, people listening. Now you're actually learning something.
Oh, yes, thank you. Just been dissed the entire class to this point. Has meant nothing. Okay, so what's going on at negative 1? Okay, so we got a min here. And we got a max here, right? And we do that from the shape, right? That's really the first derivative test, not really a test. Okay, so we could say some stuff from here. So we could say that f of x is increasing, because I think it actually asks that, right? It says determine the intervals of increasing. So it is increasing on the interval negative 1 to 1. And f of x is decreasing from negative infinity to negative 1, and from 1 to infinity, right? So we're just formalizing what's in the table there, right? Or we're enumerating, not really enumerating, we're writing it down. Right, it says determine the intervals of increase and decrease. Okay, there's the intervals of increase and decrease. Followed by determine the local max and local min points. Okay, so that's D, right? D. So we know we have a local minimum when x is a local min, when x is negative 1. So what's f of negative 1? Negative 1/2. So local min at negative 1, negative 1/2. And we got a local max when x is 1, which is 1/2. So let's say local min, local max.
Do you have to note, like, as it approaches infinity, it's 0? Do you know that is a maximum and minimum or not?
No, those are asymptotes. That's your horizontal asymptote, right? So we know that that as we're going to the left, we're dropping down to negative 1/2, and then we're going to climb back up to the axis from below, right? That was the thing we looked at, but you didn't really need to know, right? Because, you know, although, should say, and that sort of is what happens at infinity. I mean, maybe this thing does dip down, then come back up through the axis, and then dip back down again, right? Well, but if it did that, then there'd have to be another local max. So I guess that's not happening, right? But it is possible that there is one out there. So maybe as we go to negative infinity, we say, hey, we seem to be coming at it from above, right? But I know I'm dropping below. Oh, that means there's going to be another, right? There'll be a local min, then there'll be a local max, then it'll drop down again. Okay, it's all that stuff, you know, we put that all together. Okay, we got local min, local max. Determine the intervals of concavity. Okay, so what do we need for concavity? We need the second, oh, that's going to be fun. Well, it's not bad, it's just fun. Okay, so I'm going to start by just writing down, hey, here's the first derivative, right? Because now we got to do the second derivative. Okay, so what do? We start with the bottom. And go to the top. All right. That's the start of it. And now, well, what do we got? We got a negative 2x. I want to take that as a negative 2x or positive 2x? Let's take it as a 2x. I got a 2x. And I got an x squared plus 1. And that'll be negative, and then this will be minus a negative, so that'll be positive. We'll do this guy first. So we'll get 2 times 1 minus x squared, and we took this, and we took this. So yeah. Okay, and that's a minus. Oh wait, that's a minus. Is it both minus? Negative 2. Hang on. Take 2x. Yeah, I guess it's both. Negative 2 minus we need one of these guys. That. Reminder of what that was. Okay. Say it so.
So,
It's so, thank you. I feel so much better. Okay, so that's always positive. So for this to be 0, so now we're going over here, right? So we can say, well, what are we on? Oh, intervals of concavity, right? So we got to figure out where the second derivative is 0 and then look in the intervals. So the second derivative is 0 means that the numerator is 0, which is going to be 0 or plus or minus root 3, right? Because root 3 squared is 3. And negative root 3 squared is 3. Okay. And we don't care about the denominator because it's just always positive. So, what do we got? 0. No, actually. 0. Oh, no, I think negative root 3 is less than 0. Yeah, Yeah, I think so. Okay. We got a 2x. We got an x squared minus 3. We got an x squared plus 1 cubed, which is always positive, which gives us f double prime of x, which will tell us something about f of x. Okay, so this is the chart we want to fill in then, right? We have found where the second derivative is 0, which is the likely points of inflection. Okay, not guaranteed, but likely, only if the concavity is changing, right? Okay, so that's negative, that's negative. That's just 2x, right? And x squared minus 3. So if you're really big and you're subtracting 3, I think you're going to be positive. But if you're in here, it would be negative. Then that's actually kind of jumping ahead. That's part of F. So let's finish E. So concave up, where? Negative root 3 to 0. And root 3 infinity. Concave down, negative infinity, negative root 3. And 0 to root 3. All right, so I think this addresses E. And F, now we have the points of inflection, right? So F and so we go back to the original function. And then root 3. So I've shortcutted a couple of things there. I think we're good. Yeah, no, I need 30 of them.
But those nerds were
Yeah. Okay, that's F. G, sketch the, let's do that up here, I guess. Okay, so at this point we could put it all together, right? So is there symmetry? There is odd symmetry, so we could graph from 0, 0 to the right and then just reflect that. that's what kind of made this, you know, if that's negative root 3 and negative root 3, then that has to be positive root 3 just by symmetry, right? I mean, the negative of that would be negative f of x. We're coming from above, so we know that this thing is going to go like this out there, right? That's our horizontal asymptote. We have a maximum, we're at 1 1/2. So let's call that a half, negative a half, let's call that 1, negative 1. Okay, so symmetry, we've got this point and this point, right, which is the reflection about the origin. Speaking of which, the origin, I believe, is a point of inflection, as is, oh god, so what's root 3 over 4? So root 3 is like 1.7, like what?
Slightly less than a half.
Slightly less than a half? Yeah, okay, because we're maxing out at a half, so. So there's a point of reflection at root 3, so that'll be like here. And this will be negative root 3. So let's say kind of here and here. All right, so what have we got so far? Oh, asymptote, we know, well, okay, it's just going to run into all that stuff. We've got our mins and max. Oh, right, so we're increasing from negative 1 to 1. Okay, so, well, okay, increasing, yeah, that makes sense. Okay, we're decreasing from 1, yeah, okay, and then it's going to be increasing from negative 1. Decreasing from negative infinity to negative 1, right? It's going to come down to here, yeah, obviously. Okay, and we've got our points of inflection. All right, ready to graph. So this will come up to here. So this is concave down, and then it's changing to concave up as it goes out to the horizontal. This is concave up, and then it changes there. Okay, so concave up, concave down, decreasing as we come to negative 1, increasing on this interval, decreasing on this interval. All right, I think that's it. So let's see if it is. Whoa. All right, so there we go, right? 1 and 0.5, negative 1 and 0.5. There's your point of inflection-ish. Yeah, so concave down, concave up, heading to concave up, concave down, points of inflection. Nice. All right. Is that it? That's it.